right, we are ready. It's for the operator that supports our all distance classes. Ladies and gentlemen, good morning. Welcome back. I hope you had a great time at USC. So today we have the second part of our micro seminar. Again, it's a big event. The university has, I think, 50 or 60 such seminars competitively selected. The faculty proposes and the provost office select them. So just welcome back to the rocket science part. And so now let me ask our operator to switch to my laptop, please. So this is the second part, and today we will be talking about space in the 21st century. We will at first have a very global overview on the different levels, on the policy, economy, and also on the technology level, and science and technology, obviously. So we'll start on roles of space and missions. Then we'll talk about what people do in space science and space exploration. After that, we'll talk about applications in space. Space provides a lot of things in our everyday lives, even whether we know it or not. Say, for example, when you are pulling out $100 from the ATM machine, the timestamp comes from GPS satellites. So then we'll talk also about human space exploration. This is the area that is a little bit in a turbulence in our country for the last, say, 10 years. And then we'll talk about national security space. And after that, a little bit about interstellar flight. We'll discuss when are we going to land on other stars. And as I said yesterday, if you have any questions, please don't hesitate to interrupt and just ask. So space plays a major role in our everyday lives. So all aspects of our lives are affected by that. Government, business, culture. Also, many countries project their image and military prowess through space or from space, and this is also high technology. And not only that, it's also very expensive. And another very important thing about space is that it is either government controlled or conducted or government regulated. And there are reasons for that: safety and security. Because again, this is very close to the weapons. So government either directly has government-run programs, whether it's civilian or military, or if it's commercial space, it is regulated very tightly by governments. And it's obviously a highly international endeavor. As we mentioned yesterday, there are 11 countries that formed an elite club of the countries that build their own space launchers, and they launch their own satellites into space. It started with the Soviet Union and the United States, and followed by France, Japan, the People's Republic of China, the United Kingdom. After that, European countries combined their effort, and now they do conduct business through the European Space Agency in terms of putting satellites into orbit, although European countries also have some national programs that are not part of the European Space Agency. And then India, Israel launched their satellites, and finally, relatively recently, Iran, North Korea, and South Korea. And Brazil, as we mentioned, just had a program to launch a satellite. Sooner or later, they will most likely put a satellite into orbit. Also, many countries bought commercial satellites for applications, and they use them. And also, many countries experiment with space and missile technology, so obviously you have the proliferation issues, because again, this technology is close to weapons and national security. So space has many dimensions: politics, policy, science, technology, industry, entertainment, you name it. So when we talk about space exploration, space applications, or space missions, three components are required. First of all, you need to build a payload, for example, sensors or certain things that do what you want them to do in space. You put this payload on a satellite, and this satellite, or a spacecraft, or space vehicle, is sometimes called spacecraft bus. So you put them together, so on the left top corner, so this is one component, spacecraft and a payload. Then you need to launch the satellite into orbit. This is on the right side. You need space launchers, powerful rockets, again, it's a very high technological area. And then when satellites are in orbit, a lot of effort, a lot of activities, a lot of people work in this field. They control and operate satellites, and it involves communications, big antennas, a lot of computational data storage. So this is ground facilities is another major component of space enterprise. And you will see in a few minutes in terms of dollars what is happening in the world. So now if we look at astronautics and space technology, this is the field of science and engineering that deals with space systems. Everything that goes into space, and astronautical engineering as an engineering area deals with space systems, environment in space, propulsion, technology, structures, control, thermal issues, orbital mechanics. So a lot of areas of science and engineering, and because of that, in space systems we have people that are engaged. They are scientists, physicists, astronomers, mathematicians, chemists, biologists, and engineers of all possible flavors: astronautical, mechanical, electrical, aerospace, computer, chemical, just industrial, you name it. Activities in space include several areas. First of all, there's the research people do, which involves a fundamental research and applied, but also development and design of the space systems. And when I'm saying space systems, it includes also rocket launches and ground facilities, manufacturing. And the manufacturing is actually emerging as a bigger and bigger area, because in the past, the numbers of satellites were not big. You can count them dozens or maybe several dozens when the people produced, or all world produced in any single year. But now people talk about constellations of hundreds or even thousands of satellites. So manufacturing also would evolve. A lot of effort goes into testing and management. And obviously, with such a complex enterprise, a lot of other specialists are involved, like financial planners and human resources, so all kind of the supporting services that support any enterprise. Also, as we mentioned yesterday, continuing education became the way of life in some parts of the industry, in particular in the space industry. So the rocket scientists, they continue throughout their careers to get advanced degrees when they already, many of them work full-time and then get advanced degrees. And this facility here, a distance education network of the Viterbi School, actually supports a lot of such people. And a lot of short courses for the government and industry are taking place. So the people learn throughout their technical careers. You cannot, say, come out of the university and after that work successfully in your chosen field until your retirement. You cannot. You have to continuously grow. Technology evolves, the world changes, so it's a lot of things that are happening. So where are our satellites? So first of all, if I look at our Earth, just shown here, and this is approximately to scale, most of the objects that fly into space, they are relatively close to Earth. This is known as the low Earth orbit, or LEO. And the Earth's diameter is approximately 12,000 kilometers, 13,000 kilometers, something like that. So in the layer, about 1,000 kilometers thick, there are most of the satellites flying there. If you step away and just look a little bit globally at our Earth, now what is shown just right here, you will see that in addition a lot of satellites very close to Earth, there's also a belt or a ring surrounding the Earth. And the radius of this ring is approximately 6.5 times larger than the radius of the Earth. This is the so-called geostationary orbit. Satellites in that orbit would appear in a stationary position in the sky for you, an observer or customer on the ground. So if you have direct TV, technician points an antenna to this in one direction, an antenna stays without any movement for the all time of service, because satellite is continuously in this particular point. Because of that, this geostationary orbit is very crowded, and it's also one of the most valuable parts of real estate in space. So a number of satellites are located in this position. So now another very general statement is, so the most satellites are in a low Earth orbit or geostationary orbit, but there are also satellites obviously in the interplanetary space that go to other planets, but there are very few of those. Now, launch remains very expensive. It costs approximately $10,000 to put, say, 1 kilogram into orbit. So if you think about yourself to put any of you with some extra clothing and your laptop and a favorite some potato chips would cost $1 million, 100 kilos. And then when you are there, you need about 5 kilograms per day of the expendables, water, food, and other stuff. So space remains very expensive, and if the cost of access to space is reduced, say, by a factor of 3 or 4, many predict there will be an explosion of commercial applications. We still now have a lot of commercial applications already, but it will be much more if we can lower the cost by a factor of 2, 3, 4, or 5. And a lot of effort just goes into this direction, as you read in the newspapers, new companies just trying to build reusable rockets and all that, so it just works in that direction. But we're not there yet. So the scale of the global space is growing continuously. If you look at the top left corner of the table here, these are the global space expenditures, the commercial and government space. So since early 2000s, there was a steady growth, like 6-7% per year. So today it's $350 billion or something like that total. Now, government space, that means government programs, civilian as NASA in one example, and the military space dominated until early 1990s. Sometime during 1990s, commercial applications equal government space in terms of money, and today commercial space approximately twice or maybe 2.5 times larger than the government space. So commercial applications more important, or at least take more funding, use more funding than government space. So in the United States, there are 3 big space programs. Typically people think about 2 programs: civilian, like NASA exploration, astronauts, and military. This is not correct. Actually, there are 3 programs. What regular folks call military space actually consists of 2 programs. One is military, to support armed forces, soldiers in the trenches, provide navigation and all that. And another national security program is intelligence, it's reconnaissance satellites. These are different organizations, and they talk to each other, but sometimes they don't talk to each other. So in this country, we have 3 programs, and their funding is approximately equal to each other. So total, roughly, you can think about $60 billion, $20 billion NASA and other civilian space, $20 billion Department of Defense, military, and $20 billion is reconnaissance programs, intelligence community. So government space worldwide is shown here, and the United States, our expenses in government space dwarf all other countries combined, actually. So it's we account for more than 2/3 or more than 60% of the global space. So the other countries just spend significantly less, significantly less. Now, if you look at the fraction of GDP, gross domestic product, there's a big disparity how much countries spend on space. Our European friends, industrial countries in Europe, Japan, spend as a fraction of their GDP 4 to 6 times less than the United States. So United States still spends much, much more and committed to space. When if you hear somebody, and again, sometimes our European friends complain, well, United States may not want to cooperate with us. It's a question of commitment. US, again, 5 times more committed to exploration and applications in space than developed European countries and Japan, industrial countries there. France a little bit stands out in Europe, spends more than other European countries, but still significantly less than the United States. But the countries like Germany, Japan, or Italy, Great Britain, they spend significantly less than the US. They're not as committed as we are to applications and exploration of space. Now, Russia spends on par with the United States as a fraction of their expenditures, and most likely Chinese spending the same amount, mostly in the military areas, as in the same sense as the Russians do. But for China, there's no really, people have difficulty to establishing numbers because the accounting system is not transparent. And if you look at the space employment worldwide on the table on the right, again, you see that the United States employs many more rocket scientists than all other countries combined, although, again, numbers for Russia and for China, they're not really available. But if you compare again with the European countries, which are very transparent, so you would see that, again, the United States committed to space significantly more. So there's the most opportunities are there. So this is one of the reasons that people from other parts of the world, those who are really fascinated by space and want to have their careers, try to come and join space enterprise in the United States in spite of significant legal barriers, because there are certain restrictions, the ITAR regulations as they are known, that restrict participation of foreign nationals in the space program in the United States. It's because, again, of national security control. So if we look at the civilian and commercial space, what is being done there? So let's start with the civilian space, which is basically exploration, science. There are 2 drivers for exploration of space in the scientific sense. One, as a human race, we want to understand how nature is organized. What are the properties of the solar system, of the universe, what is our future. So we're trying to understand nature. This is one driver. The second driver is very practical. And these 2 areas just interconnected very tightly. So the second driver is, what are the conditions in the near Earth and interplanetary space, because this is the area where our satellite systems operate. So if we send a satellite or a space vehicle to Mars, for example, we need to know what would be conditions for this vehicle. So a lot of effort in the study what is happening in space is driven to support this practical goal. Study of the magnetosphere, upper atmosphere, ionosphere, solar wind, solar radiation. So on one hand, we want to understand how the sun operates as a star. On the other hand, the sun provides almost all energy in the solar system that drives other processes and drives the environment where our spacecraft operate. So it's, again, these 2 main drivers, understanding of nature and understanding the environment where our space systems operate and how this environment affects space systems. Then there is a human exploration. We will talk a little bit more about that, which is a big chunk, and it's very expensive also, but very exciting for the people, because, again, people relate much more what is happening when astronauts are involved rather than with some robotic spacecraft measures that absorption in the atmosphere of Saturn is 5% more than what was predicted. So it's, again, for most people would be much more excited to see what is happening on the International Space Station, because, again, a lot of space activities in space science and exploration are supported by governments or by taxpayers. So therefore, it's, again, this link is very important. So the space also does a study of the weather, space weather, remote sensing. So it's, again, we'll talk a little bit more about that. Commercial space does a lot of things similar to what government does in those areas, but also engaged in direct TV, in satellite radio, imaging. And the table on the right shows you what is happening in the commercial space. We said that the commercial space is roughly 2.5 times larger than the government space. So the commercial space is $200-something billion per year worldwide. Half of that goes into the satellite products and services, and another half goes into the ground infrastructure that supports satellites. That's why I said a lot of people work on these ground facilities, talking to the satellites and getting data or sending the data there, communicating with space systems. So now if we look at the commercial space, which is just right here, where in terms of applications, where the markets for growth or areas for growth, so you will see immediately that the most important is direct-to-home TV that dominates. After that, 4 times or 5 times smaller is satellite communications. And then Earth observation, which is growing very fast, but still very, very small compared to direct-to-home TV. So this direct TV is really the driver for the commercial space today, although other areas just picking up satellite radio, which is relatively small, but now many cars, new cars that you buy, that come with the satellite radio antennas, so it's becoming a standard. So let's now talk a little bit about space science and exploration. I already mentioned. So the people study universe. We try to understand how the galaxies are formed and Big Bang theory and all that. A lot of very sophisticated measurements are going there in astrophysics. When you study the solar system and processes, we are getting much closer to also studying the environment where the satellite systems operate. We have the sun, which is the main source of energy in the solar system. We have the Earth surrounded by the magnetosphere. It's a configuration of magnetic field of the Earth, but distorted by the interaction with the solar wind, hot plasma coming from the sun. So it's a lot of effort just going to study this relation and activities of the sun also, because our sun is variable, and the studying what around the Earth is just very, very important. So if I look at our sun, it looks just very, very quiet if you look in the visible light, basically by your eye, a light to which our eyes are sensitive. But if you look at the extreme ultraviolet to much shorter wavelengths, or X-rays, it's very, very different. So this is an example of the sun and the extreme ultraviolet, and you see that a lot of things are happening on the sun, and the sun rotates also roughly 28 days it takes for the sun to rotate. A lot of things are happening close to the surfaces, to the surface of the sun. There are also areas of the high intensities, and the solar flares may occur and all that. So I will just run it again, just note at what will happen right here in the beginning. You see there was something was ejected, parts of solar matter. This is known as the coronal mass ejection, and if this part of the solar matter hits the Earth, we have a major geomagnetic storms. In a second we'll talk about this. Also, if you look at the sun, this is the first ever detected solar quake. Just this square on the right is about that size area on the sun, and if there is a major solar flare, a huge release of energy, instantaneous release, it creates waves. So this was for the first time when it was detected 15 years ago, the solar quake. You just see, again, an enormous scale, because, again, this square is about 10% of the sun. This is another view of the solar activity. So now, if you look at the sun, it's very bright. But you can put a shield in front to block the direct solar light. And again, this is all observations from spacecraft, science spacecraft. And the solar disk is this white circle. So this dark circle blocks direct solar light. So what is emanating from the sun's surface is the solar plasma, very hot gas that is accelerated and flies in all directions. So it is known as the solar wind. So when this plasma just moves sideways, it is illuminated by the sun, and the electrons in the plasma could scatter solar light in a visible light. This is invisible. So this is what these observations do. So you can see how this flow of the plasma from the sun, solar wind, how asymmetric it is and how it changes. There are outbursts and just going in all directions. And as I said, when this plasma that is thrown away from the sun in a coronal mass ejection hits our Earth, we're getting auroras. Aurora borealis, northern lights, or aurora australis, southern lights. So these are the highly interconnected. What happens on the sun also affect what happens on Earth. And by the way, this is Venus passing by, so just got in the line of sight. In planetary exploration, there were tremendous successes. NASA spacecraft reached all planets in the solar system. They either flew by, or even orbited, or even landed. And the last planet that was not remain unvisited was Pluto, if you still count Pluto as a planet. And spacecraft 2 years ago flew by for the first time. In addition to planets, another very major area of exploration is studying of asteroids and comets. So this is flyby of an asteroid Eros, and this is not a computer animation. It's the spacecraft went around this asteroid and made a photo. So this is this movie made out of the sequence of still photos, so it tells you just how complex these structures are. And there is a lot of interest of studying these small bodies. And one of the reasons for that is the emerging area of planetary defense, and this is getting more and more attention, fortunately, from policymakers and from statesmen, and just gets more and more attention. Just think about the following. If you look at the solar system shown on the right, and this is the sun is here, and the distance from the sun is in a logarithmic scale. So our Earth is just right here, 1 astronomical unit, the distance from the Earth to the sun. This is 10 times further away, 100,000, 10,000. So these are the planets, Mercury, Venus, Earth, Mars, and so on. Now there are the two belts of comets orbiting the sun. One is known as the Kuiper belt, say from 40 astronomical units, and again 1 astronomical unit is distance from the Earth to the sun, from 40 to say 1,000. And it's like 100 million comets are there. And then there is a so-called Oort cloud, which is 10,000 times farther away from the sun than our Earth. There is zillions of comets there. If you disturb the orbit of a comet, this comet may get on a trajectory that will be coming closer to the sun. And when it comes closer to the sun, then the gravitational field of such heavy planets as Saturn and Jupiter may further change the trajectory. And some comets come as close to the sun as closer than the orbit of the Earth. That means that if you have many such objects, it's only a question of time that one of them hit our Earth. And we have geological record showing that it did happen in the past. So this is a view from space of Arizona crater, close to Flagstaff, like 30-40 miles. So this is about 1.2 kilometer in diameter crater there. And the lunar astronauts actually got some training there in 1960s. And it was caused by the impact of 80-foot diameter piece of asteroid or a comet. Only 80-foot created 1 kilometer wide crater. So the predictions are if we get hit by an asteroid or a comet 1 kilometer in size, it will finish off our civilization. And there were cases, one of them, people hypothesized that dinosaurs were wiped out when the Earth was hit by a major comet. So tracking of such objects is one of the critical tasks to understand whether some of them may come close to us or even hit the Earth, and we will find something like that. Then we have to figure out how to push it a little bit away or maybe destroy. And there is one asteroid known as Apophis that is expected to come in 2029 rather close to the Earth. And this is a pretty big piece, like 300-meter asteroid. So tracking and cataloging such objects should be a high priority. And again, it was a low priority, but because there are a lot of very important things that we want to do in space compete for limited funding. So even very compelling tasks are not getting the proper funding very often. So this is a question of just getting the right funds. So therefore, so important to educate policymakers and the politicians about that. And politicians are not exactly the people that are very responsive to such rational arguments. They have other things in their minds, as you know. So, but this is a very important problem that requires significant attention. Again, recent several years, there was a few events that contributed raising awareness. More and more money goes in that area. One of the such events was, I think, 3 or 4 years ago, where a small piece of space matter hit the Earth over a town in Russia, and there was like 1,000 people got bruises from the flying shattered glass, the window glass. So it brings attention, but it's an emerging area, and this is a very important area of planetary defense. So now if we talk about space applications, there are two main areas. The first one is communications, and in the communications area, it's the same as DirecTV. We could think about this, that DirecTV is part of the communications because it involves sending signals from the ground to a satellite and retransmitting them, whether it's a telephone calls or satellite images. So it's a big area. So it's, again, most important for commercial applications, also for national security. Another big area is remote sensing, looking down and just getting pictures of what is happening on the ground in the different spectral bands and different light wavelengths. And as an example of such remote sensing observations, I want just to show you observations of the Arctic Ocean, just simply tracking what's happening with the ice cover there. And these observations cover about 5 years. So you will see that this purple, or whatever color it is, showing ice during the winter, and then during the summer it will shrink, obviously, and then it will start growing again back as the new winter sets up. So space provides a unique way of monitoring such global processes. You cannot really do it from aircraft or from the ground observations. And in order to understand what's happening with the global climate, because there's a lot of, it's highly politicized area now, it's very difficult to tell what is right and what is wrong, but to bring science into the decisions, whatever we do, it's very important to have the observations like that covering many years, because only then you can get really global trends. And because things change from year to year all the time, in the same way as the weather. This year is different from the weather previous year. It's different from the weather that will be next year. Now, building such continuous observations is very difficult. Think about this. You put a space mission that does that. All spacecraft have lifetime. After 5 years or 8 years, the spacecraft will be dead. And what may happen, that there is not enough funding to launch the next spacecraft that provide similar observations to have this continuing database being accumulated. Or the new spacecraft that is launched has different kind of sensors that not exactly cross-calibrated. You know, there are some significant difficulties. So how do you match all data with the new ones? So this is a highly challenging area. So it's a big challenge for the space community, but the benefit is tremendous for humanity of such observations. And again, these observations on a global scale is needed for decades. Then we can really tell what's happening with, say, global climate, for example, like in this case, and how it may affect long-term the conditions. Another thing that remote sensing allows you to do, you can pick the areas even if the local folks don't want you to do. So let me just show some environmental disaster here. So there's a so-called the Sea of Aral, or Aral Sea. It's today it's on the border of Kazakhstan and Uzbekistan and Central Asia. So if you look at the big map, just it will be somewhere right here. This Europe is here, China and Russia. And in 1964, this was a very big body of water. Water from the rivers that are bringing water to this lake was taken out for irrigation, and there was some other mismanagement. So today it looks like that. You have only a little bit of water here, a little bit of water there. Again, this is to scale, these two photos. One in 1964 and another in 2000s. Now, in addition to this is an environmental disaster, there was something else. Just right here, there was an island that was the main test site for the Soviet Union to test bacteriological weapons. So a lot of this very nasty stuff was buried in the steel barrels there, and some of these barrels obviously are corrosive and leaking and all that kind of things. So in the past it was not a big deal when this island was isolated completely by water. Today there is a land bridge, so that means that the birds fly there, rodents march there, and they can, and some bad people could also get there and maybe pick up something dangerous. Fortunately, the stuff may be so dangerous if you pick it up and you don't know what you are doing, you will be dead. But still, it's a major national security issue. So unfortunately, neither the Russians, who own this place, nor our European friends that just did a lot of talking about this in the United Nations, they didn't do much to alleviate. The United States actually really stepped in and trained the health officials and the security officials and the officials in these countries here, helping them to deal with that. Because again, this is these dangerous things, and you can monitor them from space, even if the countries don't want you to know what exactly happening there. Another huge area of activities is human space exploration. So the International Space Station is a tremendous development. You think about this, it started in '98 with the two spacecraft, this one and that one, launched and docked together. So today, in 2010, there was the last module attached, last module of the phase one. Still, people plan and just bring additional pieces, but it's about 400 metric ton weight, so it's a huge station, so it's a finally operational, and finally is the time when astronauts could show that you can do real science or technology or even manufacturing in orbit, because before that time, when the entire station was assembled, just assembling it and maintaining it took all the time of the small crew that is present there. But this is a tremendous engineering achievement to put such a station, and it's also an achievement of the international cooperation, because a lot of countries are involved. The United States dominates, but a lot of countries are involved, in particular Russia, and instead, in spite of major political frictions, geopolitical frictions with the Russian Federation, still it goes pretty smoothly, cooperation in the International Space Station. So, as I mentioned, the human space flight is a little bit in a turbulence in this country for the last 10 years. So what happened, every presidential administration has a vision what to do in space. And every presidential administration, just going back to Eisenhower in the 1950s, establishes national space policy. So in 2004, George W. Bush, the President Bush, announced a new vision for the space exploration, going to the moon and beyond, returning to the moon and then going beyond to other places in the solar system. And even critics of his administration, the top policy people, praised this dramatically. For example, John Logsdon, one of the leading space policy specialists in the country, just wrote at that time that this policy for the first time really brought a coherent vision and space policy to the United States, to the space program in the United States. So what happened next is when President Obama came to office, as all presidents before him, he just changed the space policy, but typically the presidents replace one vision by another. What President Obama did, he canceled the previous vision without announcing a new vision. And we still do not know where are we going, whether we're going to, in the human spaceflight, whether we're going to Mars direct, or we will go to the moon and then go to the Mars, or we will grab this asteroid that was for 3 or 4 years was on the top of the agenda and try to bring it to the so-called libration point between the Earth and the Moon and then send astronauts to explore that. We still do not know that. And not having this vision did not help the program to stay focused, because the program depends, human spaceflight depends on people, because the taxpayers, it's not a commercial enterprise. It's taxpayers fund this, and you need support of the people, and it's very difficult to get support of people for a space program to send $20 billion per year in the United States when you do not know what you are going to do. So probably this situation would continue for some time, because what is happening today in Washington, it's not, the space is not very high on the list of priorities of the people in Washington. Let me just put it this way. But if we go back to the Bush years, so the vision was to get back to the moon. Nice video. So whenever you have a chance to speak to politicians or their staff members, don't hesitate to press them on that, although their answers may be embarrassing, but not for you, but for them. But they should be engaged. It's very important. If you feel that connection to a space program, if you want space exploration, we need to push these political people. So now let's just switch gears and talk about national security space. So you saw in the government space in the United States, 2/3 roughly activities are in national security space, military and intelligence community. So what people do in national security space? Well, first of all, it's reconnaissance. It takes a lot of effort, and reconnaissance, it's the image reconnaissance. So look at the right table. So the Corona was the first program that started in the 1960s. Then electronic reconnaissance. You pick up the signals emanating, for example, from the radar stations or the territories that you're flying over. You can reconstruct air defenses, for example, from that information. And signals intelligence. When you talk on your cell phone from space, somebody may be picking it up. Then communications. Space provides relay points for communication. So if you have a squad of soldiers somewhere in Afghanistan or somewhere else deployed, they can be talking to the headquarters in Washington through the satellites, or an unmanned aerial vehicles, a drone flies over Afghanistan. It is controlled from Nevada sometimes, again through satellite communications. Early warning means early warning of launch of ballistic missiles. When you launch a missile, you have a very hot gas coming out from the nozzle, the plume. So this infrared emission can be detected from space, and this is the key system, the key sensor from spacecraft to detect launches of ballistic missiles. The program that was deployed in the United States for many years operational is known as DSP, Defense Support Program. During the first Gulf War in 1991, Iraq fired a number of Scud missiles against Israel and against American forces deployed in Saudi Arabia. All of them launches were detected in real times, and trajectories of the missiles were determined in real time, and the warnings could be sent to the impact areas. Weather. So the national security systems also provide meteorological services. For many years, there was an attempt to merge meteorological services or satellites of the civilian world and military. So finally, I think that people came to the conclusion it's almost impossible. And one of the reasons is there's a very different requirements at what time of the day you want to observe certain area and get readings of them. For example, if you're in the Air Force, for you it's very important what are the weather at 3 o'clock or 4 o'clock in the morning, because this is where you will take off on a mission. And if you are millennial, most important for you 9 or 10 o'clock in the morning when you go to get coffee in a Starbucks. So I'm a little bit joking and exaggerating, but they're very different requirements. So finally, I think the decision was made not to merge them. Navigation, GPS, Global Positioning System, is an example. It was not designed for cab drivers today, not to be able to read maps, but just use the GPS device just to go from one place to another. It was developed for the military purposes, but GPS is an example how development of a technology leads to emergence of the huge industry now. Well, GPS is almost everywhere. International nuclear treaty compliance. A lot of sensors are flying on the satellites that would detect if a country explodes, a nuclear explosion in the atmosphere or on the ground. It will detect and pinpoint the location. So this was compliance of the international non-proliferation treaties. It's being done, and many other applications. In addition, the space technology or national security space includes support of the ballistic missiles and also the missile defense, which is a growing area. In a moment, we'll talk a little bit about that. So the American economy, infrastructure, and national security depend on satellites much more than those of other countries. So this and this very heavy reliance on space is an advantage for the United States, but also a huge vulnerability. Because other countries and sometimes even non-government actors could damage a space system and inflict tremendous damage to not only national security but also to the national economy. And this issue of the vulnerability or over-dependence on space assets was brought a number of times by very distinguished policymakers. So one of the very famous was a report in 2001. It's known as the Rumsfeld Space Commission report. It's actually commission was established by President Clinton to look into that area. And the conclusions were, and these are valid today because not much changed, the conclusions were that so we're vulnerable, our space assets are vulnerable, and we know that we are on notice, but we don't do what we should to mitigate this problem. So we are on notice, but we have not noticed. And also Commission mentioned that, as very often happens, this complacency can only be rectified by a new Pearl Harbor. The Pearl Harbor started World War II for this country, brought this country out of complacency and to address this issue, so a new space Pearl Harbor may occur, and then the situation will be addressed. So this is an outstanding problem. And again, if you just read newspapers and particularly trade literature, because trade magazines dealing professionally with these issues, they are much more reliable than mainstream media. So you will hear a lot about that. Again, it's an outstanding challenge. So if we look at a little bit at more detailed national security applications, reconnaissance plays a very important role. And reconnaissance started in the early 1960s, space reconnaissance, by a launch of a program known as Corona. And this program, it's optical intelligence taking photos. And this program was declassified, so it's a lot of photographs are available in national archives. And reconnaissance from space is very similar to remote sensing if you look down. So, and if you think about this, a lot of applications, and obviously national security reconnaissance looks at the things that are important for national security, but remote sensing, which is the same as reconnaissance, allows you to do a lot of things unrelated to national security, but very important for businesses or for commerce. Just giving an example, for example, from space, you can determine that certain plants are ready to be harvested, and then you give the command and send people to destroy this. I'm talking about a Coke, for example. Or you can monitor whether the forest is infected by some insects, whether trees are healthy or something wrong is happening. Obviously, droughts or floods can be monitored from space. Or if you trade with the commodities, for example, selling and buying oil, you can, from space, you can look at the huge tanks that keep oil and observing how temperature of different parts of these tanks changes during the day and night. Using infrared sensors, you can tell whether these huge tanks are half full or 100% full or empty. So maybe this can affect the price of oil, something like that. So it's a lot of people looking at all kinds of applications. Traffic patterns in the cities could be monitored, and you can help in the management of traffic. So all kinds of things you can learn from space. One of the examples that I have here just from this Corona program, they could help archaeology. This photography found the area that had remnants of the camp of the legion, of the Roman legion in deployed in Jordan 2,000 years ago. So it's a lot of things can be done from space, and the reconnaissance is just a huge area. Again, 1/3 of the U.S. government space program is going there. Military space, supporting the people in the uniform and the operations of the various units, involve communications. As we talked, just provide secure communications between the units and also with the presidential authority. Navigational systems are very important. Then weather meteorological satellites, nuclear treaty compliance verifications. Satellites were in the past, now it's sensors on many other satellites. And early warning detection of rocket or missile launches. These are the huge satellites defense support program. And the role of military space continues to grow, and many other countries are becoming more and more active. Obviously, Russia is rebuilding its capability. China is advancing very much. India also starts building up because India cannot afford to have China be much stronger. So it will be competition there. Just no matter what Chinese would do, India would try to match. And European countries also be getting more aggressive or active in space. So now, let me just talk a little bit about missile defense that will continue to grow its importance. And missile defense, in particular, last month is just all over the place now in the newspapers with the threats coming from North Korea. So the idea of missile defense coming from 1950s, but the challenge was so huge to hit a small warhead moving with the extremely high velocities, 5-10 kilometers per second. So this was the challenge of intercepting such a warhead was compared to hitting a bullet with another bullet. So many people thought it's technologically not possible, but others persevered. And the first intercept actually of ballistic missile, long-range ballistic missile, was demonstrated in 1961 by the Soviet Union and the United States. Just in 15 months, roughly 16 months, demonstrated a similar intercept, and even some missile defense systems were deployed, although they are not really 100% effective. So the reason for missile defense to stay is that the ballistic missile threat expands. Think about this. In 1972, there were only 9 countries with ballistic missiles. By 2006, we had 25 countries with ballistic missiles, and exchange by ballistic missiles occurred in 6 regional conflicts. Probably the biggest was the war between Iran and Iraq in the 1980s. They were shooting Scud missiles or the equivalents at each other for many hundred miles. So on top of that, there is a proliferation of nuclear weapons. So if you can mate a nuclear weapon with a missile, you can threaten basically any country in the world, as we see today North Korea does. And the space technology proliferation also plays into that, because it's a very related technology when you build ballistic missiles or space launchers or interceptor missiles. So the same kind of technologies are involved. So the missile defense involves, and by the way, the budget of missile defense in this country is roughly 1/2 of the NASA budget, but again, the missile defense would continue growing. So the missile defense includes 3 components you hear occasionally in specialized publications, or if somebody knowledgeable talks on TV, which is very rare occasion. There's a boost phase defense, where you try to intercept or destroy a launcher during the first few minutes as it slowly moves from the launch sites and accelerates. Then there is a terminal defense segment This is when already the warhead comes to the area to hit, and you just try to intercept it at the very last stage. This is the U.S. THAAD, T-H-A-A-D, battery deployed in South Korea recently, with a lot of controversy that you heard in the newspapers about that. This is for the terminal defense segment. And then there is a mid-course defense segment. Basically, a warhead flies through space, because the warheads fly at the altitudes 4,000 or 5,000 miles above the Earth. So they're in space, they're in a spacecraft. So, and intercepting them in mid-course, this is done by the mid-course interceptors, those that you read in the newspapers. If you follow that, when the battery deployed in Alaska, 30 interceptors and 4 interceptors deployed in California, the Vandenberg Air Force Base. So these are for the mid-course. So this is if North Korea shoots at the United States, so just to try to intercept them. So this is for the mid-course. So it's a different systems, different radar systems, a lot of satellites with the sensors, a lot of communications that fuse from different sensors, the information coming about possible launches. So the interceptors, they are ground-based. They're also sea-based on the ships, naval ships. They're air-based, are being considered maybe to create special UAVs, unmanned aerial vehicles that would be involved. Again, this is in the future. And the space-based interceptors that was part of the President Reagan's Strategic Defense Initiative. Some technologies were developed, but it never got to implementation, but it may come in the future. So missile defense is an integral part of the space technology space, and it will stay here given how the world is evolving and can only grow. So let's have an example of the intercept in 2007. So the test missile was launched from Alaska, from Kodiak Island there, and interceptor was launched from Vandenberg Air Force Base, 150 miles north from Los Angeles, just a little bit north from Santa Barbara. So this is the launch of the missile to be intercepted. And space technology, again, comes in a various part of missile defense: intelligence, reconnaissance, sensors, communications, navigation, missiles, propulsion, basically everything. So this is the area for rocket scientists and rocket science. So as the missile went up, so after some time...
5, 4, 3, 2, 1, 0. Have a launch. Interceptor away.
So the radar detects the missile to intercept, determines where it is, and then the interceptor is being launched. And then you have to hit a bullet with a bullet, because it's simply a collision, mechanical collision of one body with another. You don't need to carry explosives on the interceptor, because the kinetic energy is actually of the intercept, just due to the relative velocity, is bigger than if you put TNT there and explode. So it's just simply a question of navigation. Just make sure that you hit head-on the missile. Now, staging view here means it's a two-stage interceptor. So when the first stage burns out, it drops. And then you see this bright part was just slowing down, and then the intercept itself continues. And now infrared cameras just follow intercept, and you see the hit. Again, this is a little bit simplified, because if you're a bad guy, you will try to deploy decoys also and all kind of countermeasures. And in the military technology, it's always a competition between your weapons and counter weapons. So it's an ongoing competition. So now just let's talk about something that creates issues and brings a major challenge to space for everybody, whether it's national security, human spaceflight, and applications. It's a space debris. The number of objects orbiting the Earth increases, and if you have too many of those, they may accidentally collide. And this obviously will create, every collision creates, instead of say one big piece of something that is flying, space vehicle or rocket stage that's flying in orbit, so when they collide, it disintegrates in 1,000 of smaller objects. And the relative velocity of the collision in orbit between objects is about 10 kilometers per second. This is 30 times higher than the velocity of a bullet coming out of a handgun. And you think about this, you know how much damage a bullet can inflict if it hits something. So now you have velocity 30 times higher. That means energy, kinetic energy on the collision is 1,000 times higher than the kinetic energy of a bullet. So small piece of debris, then it hits a satellite, it will damage the satellite beyond repair. So even just small pieces just could wipe out many space systems, and it's obviously it's a danger for astronauts when they go in the extravehicular activity, because the spacesuit can protect against sub-millimeter parts of the things that are flying there, but then against larger things they cannot protect. So when astronauts go there, there's a probability always that some of them will be killed. Not may be killed, will be killed. It's only a question of time. It will happen. So these people take their chances. So always just remember they're really brave men and women just go there. So if we, a lot of statistics available on space debris, in particular the objects larger than 10 centimeters in diameter, basically larger than a grapefruit, are all 90-something% are cataloged. We know where they are at every given moment of time, but only 10 centimeters and larger. The smaller one, like a bullet, which are hundreds of times more numerous than the larger objects, they are not cataloged. This is a pure probability now when you fly a spacecraft and it may get hit. So the cataloged objects are shown here since the beginning of space age is 1957. So the black curve is the total number of the objects there. So today about 20,000 such objects are cataloged. We know exactly where they are. And knowing their orbit, you can do what is called a conjunction analysis. You can see whether your spacecraft have a chance to collide with something else, say in a week or in 10 days. And when you see that it just may collide, then you just try to maybe do some maneuver, just put it away. Now, so we're trying to reduce the number of objects, new objects that are being created in space, but unfortunately, certain things are happening beyond our control that increase these numbers. In particular, there was a very egregious case in 2007 when the People's Republic of China conducted the anti-satellite missile test. They basically sent a missile from the ground and hit their old defunct satellite and destroyed it to demonstrate that they can do this. And it created 25% more debris than that we had at that time. So they increased in one accident. And another accident happened in 2009 when the two satellites collided accidentally. It's American Iridium and one of the Russian Cosmos satellites. Just by accident, they just collided. It's, when you have so many orbits, so many objects flying around the Earth, it's only a question of probability that some of them collide. So this also increased, as you see right here, increased the number of debris. So when Chinese did their tests, so they created a cloud of debris out of the satellite, and these debris were tracked on the catalog, and then you can put this in the computer model to show how this cloud, red dots of created debris, propagates. A major concern obviously was for the International Space Station. You just don't want astronauts to get hurt, so you will see the space station. So these are the computer simulations, but the debris were real, measured, their characteristics measured, their trajectories measured, and then the computer can simply show where the particular piece of debris will be after some time. So this is a big challenging issue with debris. It's becoming only bigger. All countries are affected, and all countries are contributing into that. So it's a big challenge for the space community to find a solution. To remove stuff from the orbit is very expensive. It's almost as expensive as put things there. So somebody has to foot the bill, and this is something that nobody knows how to do this. And finally, a few words about interstellar flight. Our technology is not ready to go to other stars, and nobody knows when it could happen. However, people are talking about putting, for many years, NASA had on the books for like 30 or 40 years a mission known as the Interstellar Probe to put a spacecraft into interstellar medium surrounding the solar system, and the medium that not really disturbed by the presence of the sun. And this means the distance about 300 or 400 times farther away from the sun than our Earth. So 350, 400 astronomical units. So the sun is here, Earth, Mars, Jupiter, Saturn at 10 astronomical units. Then there is a region where this solar wind, hot solar plasma, collides with a very cold and dilute interstellar medium surrounding the solar system. It's approximately at 100 astronomical units. And Voyager spacecraft, they are shown here, Voyager 1 and Voyager 2, just leaving the solar system. So that an idea is to send a spacecraft a little bit farther away, 300, 400 astronomical units, and to do sampling of the interstellar medium. Now, the mission is doable, but it's very expensive. It's probably $1 billion or something like that. Would cost, and but again, NASA studied this for 30, 40 years, and this mission competes against other very compelling scientific proposals. Remember, I said that people want to do in space many more things than the funding allows to do with all this competition. So in the meantime, we learned a lot about this interaction region, at least about interstellar boundary of the solar system from Voyager spacecraft. And also in 2008, NASA launched Interstellar Boundary Explorer. It's a small spacecraft orbiting the Earth. They had special sensors. And these sensors mapped this interstellar boundary. And I'm a co-investigator on this mission and one of the instigators, actually. And we discovered something in this boundary, some feature that was not predicted, and this put us actually on the cover of the Science magazine in 2009. So it's so we know something about this region, and we continue to push and develop technology to get farther. And currently, the two main technologies that are being considered, one is so-called RTG-based, which is radioisotope thermal generator-based ion propulsion, basically produce electrical power using these radioisotope thermal generators and use electric thrusters to continuously accelerate spacecraft. Now, we can do this, but one of the challenges is that you want to reach this region, 300 astronomical units from the sun, within, say, 25, 20 years after the launch, which is the lifetime of scientists, or a human being, professional life. So you cannot plan and build a spacecraft that would reach it in 200 years. Voyagers would get there in 100 years. But it's the people who conceived the mission, they won't be alive by that time. So we would like to have something that to build technology, accelerate a spacecraft, space vehicle to such a velocity that at least graduate students that were involved with the people who built it, they will be still around and will be able to control the spacecraft, understand instrumentation, sensors, and understand the science that will be coming out. So one of the approaches, again, was this electric propulsion. And the second one that is being considered, but technology is not there yet, is the solar sails. one of the ideas that, and I was involved in all these activities for many years as a part of my job. So with the solar sail, like 15 years ago, when we considered, the idea was to deploy a sail about 300 meters in diameter, slowly spinning for stability. And at first you position solar sail in such a way as to decelerate the spacecraft, and it will start falling towards the sun. And when you get to approximately a distance, 20% of the distance to the Earth from the sun, then you turn this flimsy 300-meter diameter rotating solar sail and start accelerating the spacecraft. So it's a lot of very cool things that could be done, but it requires billions or hundreds of billions of dollars. And people do a lot of exciting stuff. So in the meantime, we cannot still go to the nearest star, Alpha Centauri, but there are a lot of other things that could be done, and a lot of in applications, in exploration, in human exploration, in understanding nature. So space is a huge area, very exciting. A lot of smart people are working there. It's a rocket science and the land of rocket scientists. And the road to Alpha Centauri is not easy, and through difficulties to the stars. So this is all for our seminar. So if our operator is still there, he needs to change camera. Thank you. So guys, thank you very much for coming, and just make sure you fill these evaluation forms. And if you have any questions, we can just talk. And by the way, I can tell you whatever you want to know about campus, because they will stop recording right now. I can tell you the real story.